Okay, this is known as the counter twist. So what this counter twist does is like what you have seen down here. It eliminates the what? The twisting. Okay, so we got rid of the twisting, right? We got rid of the twisting. So when we got rid of the twisting, right? When we got rid of the twisting, then when after eliminating the twist, right? Then we can apply the shear stress is equal to VQ over IT, or the shear flow is equal to VQ over I. Okay. So let's see what is going on. Okay. Let's see what's going on. So originally, okay. So I'm going to draw scenarios cases now. Okay. Originally, okay, with twisting, right? So this is the original. Okay, this is the so with twisting. So what we have over here is we have the same structure. So we have this is our centroid, okay, and this is our the other centroid. So let's say now, okay, for example, not for example, like we have this condition now where over here, right, where I put our arrow over there, that is our shear force V. Okay, that's our shear force V. And we know the structure will twist, right? We know that the structure will twist, right? So the structure will want to twist this direction, right? The structure will want to twist the original. So when that's a case, right? When that's a case, if we were to draw our shear flow, okay, we're going to control our shear flow. Our shear flow will go this way, right? And then why I draw the web first, because it's the web that controls the direction of the shear flow. Yes or no? If V is in this right direction, the shear flow on the web will be coming down. So then we draw our shear flow now. Okay. Right. So this has a twist. Okay. So the only way to eliminate the twist, okay, to eliminate the twist, we have to do something else. Okay. So in the horizontal section, okay, in the horizontal section, okay, horizontal section. Okay, so there are two horizontal sections, or we call them the flange. Okay. The force over here will be known as F in the horizontal section. Down here will also be known as F, right? The vertical one, so for the vertical section, or for this case, we usually call them as a web, right? We call the shear flow, we are going to label the force to be V. Okay, we just call it V, right? So again, the horizontal section is what we call flange. Okay. Okay. Now we are going to have an offset. Okay. So that's the original. So now there's a twist. Now we are going to eliminate. Okay, eliminate the twist. Okay, eliminate the twisting. So what we are trying, what we do down here to eliminate the twisting, this is what we've done. Okay, so now, okay, I'm going to draw the same cross section. Okay, so I'm going to draw the same cross section. Right, so we still have our F down here. Okay, we still have F down here, right? And what we have done, because we have artificially, what? We have artificially put a block, yes or no? We have artificially put this block over here that I've drawn, okay? This block over here that I'm shading now, okay? We have artificially put a block over there. So what that generate is this, okay? So if this is the center line of the web, okay, we are putting a V over here, okay? And I'm going to call this point, this point over here, I'm going to call our point C, okay? And the distance from here to here is known as E, okay? And E over here, so this is still our F, right? The E over here is what we call our shear center. Okay, that's all. So it is this V multiplied by E, right? This term over here, we are going to what? Eliminate. Okay, so it's going to what? This term over here will eliminate the twisting. Okay, this term over here will eliminate twisting. So let me write a bit. Okay, so if we come back to the original diagram, before that, any question? Now don't worry, I understand that this is very abstract, okay, but the calculation is not going to be any more difficult than what you have done already. I repeat again, the calculation is not going to be any difficult with what you have done. Okay, you guys have reached a Zen level already in shearing stress. Okay, so the O position, okay, so I'm going to call this the C position, okay, or okay, this point over here, okay. So wait, let me see where's the O. No, I'm not going to write that, okay. So now the thing is this, the distance E, okay. So I'm going to write this out. So to remove the twist, okay, to remove the twist, right, the shear force okay, the shear force needs to be applied. It needs to be applied at a certain distance away, okay, away from the structure. Okay, so the distance E, what I've shown you before, the distance E is also known as the shear center. Okay, it's also known as shear center. So to calculate F, okay, to determine F, okay, to determine F, all you need to do now, okay. So if I were to call this, point A, over here is point B, okay, that's my point A and that's my point B, and the distance from A moving to here is what we call S, okay. So F to F prime, or F is equal to the integral of point A to point B, right? The shear flow Q, okay, multiplied by ds. Okay, so this is our shear flow. Okay, And then if we are going to use shearing stress, okay, so again, this can be A and this can be B. Then all you need to do is the shear stress multiplied by the thickness, okay, and then yes, okay, so this over here, you just have to include your thickness, okay. So now let's base our analysis from this diagram, okay. So let's base, I'm going to put in this diagram now, okay. We're going to have this diagram, okay. So you guys are copying. Let me zoom out so some of you are still writing. You can still write. Okay. So if we're going to use this diagram now, okay, we're going to use this diagram. Okay. So I'm going to label this diagram. Okay. So over here, at a point over here, right, the distance from here to here, I call it h/2. Okay. So this is exactly at the center line over here. Okay, exactly at the center line over here. So that is our h/2. Okay, that is our h/2. So we have a force going in this way, right? We have a force F, okay, coming out will be the other direction. The other F will be below us, right? And then we have V, okay, and then we are going to take. So if I will draw our transformation again, this over here is our, oh, sorry, someone asked a question and I did not see it. Is the C in the second diagram the centroid or the center of the web? It's not the centroid, it's the center of the web, okay, to Yurin Chan, okay. Eugene, we are using the 6th edition for the textbook. Let me check, is it the same section later on, okay. Now, so what we have now, so this center over here, I'm going to call my point C, okay. So this is my Y, this is my X, Z, okay, and this is our rotation in X, okay, that's our rotation in X. So what I'm going to do now, or what we're going to do now, is we are going to take summation about moment, right, in the X direction. We're going to take our moment at point C, okay. So the computer crash again, my bad. Sorry, let me fire it up again. Okay, hopefully nothing shifted. Yeah, nothing shifted. Okay, we are going to take moment in the X direction. Oh, before, what is the difference between VS analysis? This VS, Oliver, what do I mean by VS analysis? This is torsion in the beam. Oliver, where are you? Can you speak, Oliver? Oh, versus. Okay. What is the difference is when you guys were learning beams, they are thick wall. This is thin wall. Okay, this is thin wall. So thin wall, you have to apply this theory. Okay, when it's thick wall, when it's unsymmetrical, then you can apply the other theory. Okay, torsion of the beam. Oliver, is that okay for you, Oliver? Okay, and most of the time, what you learn in torsion is all in what? Round, yes or no? Right, most of the time it's round. This is not round. Okay, but by the way, you can do torsion analysis also. But as I say, you can do torsion analysis even though your beam is not round. You can, okay, and you also can do when it's not a thin wall. I'll show you guys that, okay. So, but I don't think Dr. Koshi, okay, I don't think is outside. I don't think you all learn with Dr. Koshi on this. Let me get the textbook out. Okay, let me get a textbook out. Let let me show you in the textbook. Okay, there we are. So if you look at chapter torsion, I think it's chapter 3, right? If you look at torsion, okay, so if you look at a torsion, okay, so you have a structure like this now. Okay, let me show you where. Yeah, so our formulas like this that you need to apply, okay, which Dr. Koshi, I believe, did not touch at all. Okay, so these are for non-round bar, but it's not difficult. Okay, as I said, it's basically using a shape function. Okay, so you see, you have square section. Okay, so you have thin wall analysis also. Okay, so you can use this sort of formulas also. But the thing about this sort of formula, the structure has to be a closed circuit. You get what I mean by closed circuit? It cannot have an open channel. I will see. I don't think over here they will have anything open channel. Wait, let me go one page down. Yeah, it's all closed channel. Okay, it's all closed channel. You only can apply what you learn over here. Okay, what you learn over here, if the structure is closed channel. Okay, so what we have now is not a closed channel, it's an open channel. Oliver, does that make sense to you, Oliver? I hope he's okay. Yeah, I think he's okay. Yes, okay. So you are satisfied with your answer? Yes, Oliver? Good observation, Oliver. Okay. Right, now let me get back to our lecture. Okay, now let me get back. Okay. So moment about X, okay, at point C has to be equal to 0. Okay, it has to be equal to 0. Okay, so by doing so, we are taking moment over here. Okay, so anything that's anti-clockwise is positive. That is what we are declaring over here. So the first F, come on, Eugene, is H over 2. Right, so this one is going in a the first F over here is going to generate a moment about point C that is anti-clockwise, so it's positive. So force, okay, F multiplied by H divided by 2. Okay, and then the bottom one, the same thing, plus by F multiplied by H divided by 2. Okay, so now we have the V, same direction, V multiplied by E, and the whole thing is equal to 0. Okay, so if we look at V multiplied by E, right, or V multiplied by E, okay, is equal to FH. So the shear center is equal to FH over V. Okay, so now we know the distance of the shear center. By the way, I do make a mistake over here. This should be minus FH, right? So minus FH over V. When it's minus, why is minus means it's going to the left-hand side relative to point C. Okay, if it's positive, it'll be on the right-hand side relative to point C. Okay, so with the shear center, so now once we find the shear center, right? So with the shear center, okay, with the shear center E, right, the structure will deform without twisting, right? Then we can apply the formula where shear stress is equal to VQ over IT. Okay, we have to eliminate the twisting. Okay, so I'm going to stop my lecture here. I'm going to talk slightly about one of the problems that we have in our homework. Okay, so a student asked this question before I started. Okay, before we started. So our it will not take more than 5 minutes. Okay, it will not, or 2 minutes. Okay, so a student asks, homework 7. How y'all find homework 7? Anyone? Anyone can tell me anything about homework 7? Anyone? Or you have not tried yet? Anyone? Okay, well, you know what? I will stop recording. Then you can be more verbal.
Oh, Professor.
Yes.
I'm sorry, I didn't mean to interrupt, but before you stop recording, I just wanted to ask something. Well,